Precalc 1.2, exponents and radicals. So, what we have here is, remember, what does it mean to have an exponent? So what does it mean when I say a squared, or a to the 5th power, or 2 to the 10th power? What does that mean? It's kind of listed up there. But what are we doing? When I say a to the 5th power, what is it? Yeah. Yeah, a times itself 5 times. So essentially, what we're looking at is that any variable that has a power on it, yeah, that's a to the n, you just have to multiply itself, the base, n times. So whatever n happens to be, you just keep multiplying across. So, yes, a to the 5th power is equal to a times a times a times a times a. We should know that, and that's kind of why they cancel when you have something like a to the 5th over a squared. 2 of the a's will be able to cancel, and you're left with a to the 3rd. That's one of our exponent rules, or laws, as they're calling them in this book. There are 7 of them. Now, I'm not going to be stickler on the name per se, power of a power, product of powers, a power of products, those things. I want to know, can you recognize a law being used? Can you use it correctly? So, who's got one? Whether it's by name or they know what it looks like. Here, I'll help you guys out. I'll do the first one. A to the n times a to the m. Does anybody know what that one's called? Product of powers. You're multiplying things that have powers. These powers have the same base. Bless you. And so, if you're multiplying something with the same base, what can you do to their exponents? Add them. So, we end up with a to the n plus m. What's another one that would be the other way then? Yeah. Right. A to the n over a to the m, which would result in what happening? Subtracting the exponents. Do we have another one?
What's that called?
This one is the quotient of powers. That was the quotient of powers, dividing of powers. Power of a power, which one was that? Power of a power. No, that was the first one was product of powers. Power of a power.
You multiply the exponents.
You multiply the exponents, what does it look like?
It's like parentheses and then a to the 2nd or something.
Okay, we're going to make it very generic, so we'll put a to the n inside. What goes on the outside? M in our case, because we're using the same variables. So that's a power of a power. So power of a power, you, like we just said, multiply. Okay? And there it means there's 4 more. What happens if I had some stuff inside a set of parentheses and I have an exponent on it? This one's called what? The distribution one? No. This one's called a power on a product, power of a product. Yes, okay. Guys, this acts like we're distributing the exponent because the n has to become a power on a and b, but you're really not distributing. It's not how it's officially done. But it looks like we're doing that. And so you end up with the result of a to the n, b to the n. Again, that's power of a product. We also have power of a, not multiplying, but dividing. That's power of a, starts with a Q, quotient. And the same process, right? The exponent goes to the top and it goes to the bottom. Two more. The next one is the one that everybody likes, but half of us will get wrong because we end up making a mistake. Because we, for some reason, think we want to multiply, and it's not really multiplying. The zero exponent rule. Anything to the 0 power is equal to 1. Yeah, it's not 0. It is 1. 0 to the 0 power? I do believe that still would be, that one might be undefined because you can't divide by 0. Quick little proof here, guys. If I asked you what 1 is equal to, I think most of us would be okay with saying, hey, that's just 4 over 4, right? This is not a true proof. I'm just trying to give you guys a little idea here. Using our rules over here, I think you guys by substitution would be okay with 2 squared over 2 squared. That's okay? Wait a minute. Can I use rule number 2 we have up there? And since they're the same base, what can I do to those exponents? So that'd be 2 to the 2 minus 2, which is 2 to the 0. And so ends up being 1. So it's not a true proof, okay? Because I used numbers. You can't prove something with one example, okay? But I was able to kind of say, hey, I could start with 1 and end up with something to the 0 power. So anything with a 0 power is going to be 1. The 0, 1, I know the answer to this. I've looked it up before. I'll have to get back to you on that one. But I want to say because if you have 0 on the bottom, it's undefined. So I think that might be one of the exceptions. Last one. What's the one thing we did not touch upon? Negative exponents. So a to the negative exponent, what do we do to it? If it's on top, we bring it to the and make it a positive exponent. Now, I find that a lot of students get mixed up on this one because if there's multiple things going on top or the bottom, they want to take all of it. The only one that gets to move is the one that has the negative exponent. Now, I also like to add to this one is what happens if the power is negative on the bottom. It goes to the top and just becomes a to the m. So there's options, guys. Anything that has a positive exponent on top, you could just move it to the bottom when we're multiplying things and make it a negative exponent if it's going to be helpful for us. So it's all about trying to find the right combination of things to make things simplified or help us out. And again, you only move the one that has a negative exponent. If the negative exponent is on a set of parentheses, that whole parentheses gets to move down or up, but not if it's just on a single number or variable. So to kind of talk about that whole idea of negative exponents, what happens if it's a negative exponent on a fraction? They just kind of in the book say, hey, we got some laws of exponents here, some more of them. And it's just if you raise a fraction to a power, what happens is the fraction flips. That's the coolest part. Or essentially, as in here, this negative exponent, I could bring it in, right? That was the power of a quotient. And I'll have a to the negative n and, well, that's never mind. That's two different variables. But basically, why 6 works is because this becomes a to the negative n. I'll write that down. A to the negative n over b to the negative n. Well, what happens with each of those? They both have a negative exponent. So the a goes to the bottom, the b goes to the top. And that's why you end up getting the fact that you have this. So instead, I'll just bring the negative in, flip it, take the reciprocal. So negatives are the reciprocal of fractions when it's an exponent. Essentially, that's what's happening at the bottom one. You're just flipping sides, as you can see. So that's pretty straightforward. We already kind of talked about that a little bit. No need to keep going. So let's do some examples of this. Let's practice. Try them on your own, and then we're going to come back together. First question, what's the first thing I should do?
Figure out the exponents.
Figure out the exponents, as in what? It's all about exponents, right? It's all about those exponents. Second one. Okay, right. Guys, do you guys recognize that the first one, there is nothing outside that parentheses? Do I really even need it? No. So maybe I just want to get rid of that. For me, I always like to try to get rid of parentheses when I can because sometimes it just makes things more troublesome. Second one, what do I have to do with that set of parentheses? Because there is something on the outside. What's that? Multiply the exponent to all the other exponents inside. So bring the 3 in, right? So this becomes 3 to the third power. Don't forget that constants also have to be multiplied or have that power of a power idea. A to the third and b to the 12th. At this point, they're all multiplied. Now we can go to our multiplication rules. Can we all do this? 2 times 3 to the third power. 3 to the third power times 2. Which is what? 54. Putting all the numbers or constants together. Then we got a to the third power times a to the third power, which is a to the 6. And b to the 14. Yay or nay? Awesome. So far, so good. Hey, what happens if I have a fraction now? To me, when I'm working with fractions, I always want to simplify 3 different times. I want to simplify across the top first, simplify across the bottom second, and then I will simplify up and down. I don't want to, now, granted, it's not the only way. We could just go and hunt for all the numbers first and do all of those, do all the constants, and then the s's and then the t's. But I'd rather just take them one step at a time. Move things where I need to, so forth. So, across the top, can I combine anything on top? A 6, an s, and a t. You can't. They're not like terms. But I don't like something. What don't I like? The -4. So, the first thing I would do is say, hey, that t to the -4 is now to the bottom. Or now, whoops, what did I do? T to the 4th gets to move to the bottom. Yes? Then I'm going to go to the bottom. 2 is not going anywhere. I'll put a 2 back in. S goes to the top, so it's s squared on top. And t squared, t2, still there. And at this point, now we can gather up like terms, right? Oh, wait. I just created some more work on top and bottom, didn't I? I have s times s squared, which gives us s to the 3rd, t to the 4th times t squared. And maybe I think most of us should be able to see that we have 6 divided by 2. And that should go on top, right? I mean, we take things at different times. We could have done that first because it was way out front in the beginning. But we get 3s cubed over t to the 6th power. Next thing that's going to be very helpful for us is scientific notation. Remember, scientific notation is a compact way to denote very large or small numbers. It's in the form that you have a number between 1 and 10, right? Can be equal to 10, but not to 10. So basically, 1 to 9 point something, where n is an integer, power, times 10 to some power. Basically, remember, when you multiply or divide by tens, your decimal point just moves left or right. And so, there are 2 things that you guys are going to have to do in your homework. You're going to have to, number 1, start with standard form, which numbers that we always have seen, and convert them to scientific form, and go from scientific form back to standard form. Not so bad. So our first 2 problems here is to convert to the other form. First one's in scientific notation. Next one's in standard. Wait a minute. Is that really already in scientific notation? It's 85.4. What's wrong with it? It's bigger than 10. So therefore, I need to move that decimal place to where? 1 to the left. Now, some of us already know that if I move it to the left, I'm either going to add a number to my 10 to the 6th, so it's either 7 or is it a 5? But some of us are just not going to be able to remember that. So I'm going to teach you or have you guys do a little bit more work. If you're to the point where you don't need to do it, that's great. But I say, number one, convert it. Actually, this one you actually have to convert, so it's not like you have to. But I would say, convert this to standard form. So you take your decimal and move it 1, 2, 3, 4, 5, 6, right? So 8, 5, 0, followed by 1, 2, 3, 4, 5. Nope, 5. 5 zeros. And so you get 85,400,000. Sorry, for this particular problem, that is it. But if I had to actually convert that to proper scientific notation, I need it to say 8.54, right? So I would have converted to standard form, and then from standard form convert it back. And when you convert that back, you know that you will be counting 1, 2, 3, 4, 5, 6, 7 places to get back between the 8 and the 5. So when you're moving your decimal to the left here, it looks like you're adding to your exponent. So when you move to the right, you'd be subtracting. I like to sometimes think of it as, do I have to go further? That means I have to raise my exponent. If I'm going less further, then I can lower it. So when I'm going on part B to scientific notation, we know it should be 2.84. At least I hope everybody recognizes that. And it's going to be times 10 to the what? 7. So there we go. Those are easy when you just have to do them individually. But part C, that's when things start to get a little bit interesting. We can use scientific notation to our advantage because if I convert everything into scientific notation, I have a number times, this is one of the few times still that we will use x as multiplication, times 10 to a power. So it's just a number times a number, right? And if I multiply numbers times numbers, and I multiply it by another scientific notation, everything is multiplied. And from, I think it was from our other lesson, multiplication is commutative and it's associative. So therefore, I can multiply numbers in any order I want. We're going to use that to our advantage. So in part C, convert all 3 of those numbers into proper scientific notation. So 4.6 times 10 to the what? -4. The second one actually already is right, correct? And, oh, that one's also nice. Okay. So they're all in scientific notation now. Now, what I'm going to do is I'm going to take my calculator, because most of us probably would take a little bit too long to do. I need 4.6 times 1.697 divided by 2.91. I am going to take the numbers, the ones without the exponents, and multiply across the top and divide by the bottom. Give me, let's see, what, 3? Let's just do 3 decimals. We're not doing any kind of significant digits or anything like that. So what do we get? I'm assuming somewhere around 2 something, right? 2.68. Others hopefully verify that. Then, that's really the only part where you should probably need a calculator. Because now, all you have to do is look at our exponents and say, okay, when they're on top and I'm multiplying 10 times 10, I can do what to their exponents? Add. So therefore you get -4 plus 22 is 18, and then you're going to subtract the ones on the bottom. Wait, I'm going to subtract a -18, which means I'm going to add, which then ends up being 18 plus 18, 36. That is a very large number. I think most of us would agree. That's pretty big. Now, not every time does it come out to 2 point something or something point something. Sometimes it goes back to the 85.4. Convert it to standard, convert it back. Your homework for 1.2 day 1 is page 23, 23 through 50, every 3, 69, 71, 78, and 79. Have a fantastic day.